Hello everyone, welcome back to my channel. Today we will be solving Unit 3 for May 2024 of IAS. So let's start. This is a question about practical activities involving the collection of a gas. A student used the apparatus shown to collect the gas produced from the reaction between copper to carbonate and sulfuric acid. Okay, so basically sulfuric acid and copper to carbonate are going to react to produce carbon dioxide, right? The bung was removed and 0.650 gram of copper to carbonate was added to 25 cm cube of 2 mole per dm cube sulfuric acid. So this is the information, this one, and this one, right? And the bung was quickly replaced and 120 cm cube of carbon dioxide gas was collected. 120 cm cube of carbon dioxide gas was collected. And the equation for the reaction is shown. Calculate the molar volume of carbon dioxide. Okay, so molar volume of carbon dioxide. I know the volume. All I need to know is, first of all, I need to find the moles of copper to carbonate, right? So mole of CO3 is equals to 0.650 divided by molar value, right? So it is going to be copper is 63.5 plus carbon is 12 plus oxygen is 16 times 2. Sorry, 16 times 3. Okay. So if that's the case, let's see what is the value. So 0.650 over 123.5. This gives us 0.0052632, right? So we will take we will write down 5.26 into 10 to the power minus 3. 5.26 into 10 to the power minus 3. 5.26 into 10 to the power minus 3 moles. Now the mole ratio of copper to carbonate and carbon dioxide is 1:1. That means the moles of CO2 is equals to 5.26 into 10 to the power minus 3. It's the same. So now since we know the moles, so we also know the volume. We can calculate the molar volume. So moles is equals to volume over molar volume, right? So if I subject molar volume, molar volume is going to be equal to volume is 120 over mole, which is 5.26 into 10 to the power minus 3. If you press in the calculators, you will get the answer as 22800 cm cube, right? Now the answer needs to be in dm cube, so we divide it with 1000 and we get 22.8 dm cube per mole. That's the answer. After reaction, tests can be carried out on the mixture to show that the sulfuric acid was in excess. State the observation if a small volume of sodium hydrogen carbonate was added. Okay, so sodium hydrogen carbonate is going to react with the HCl or the acid. Over here, I guess it's not HCl but H2SO4. Yeah. So with H2SO4, hydrogen carbonate will react to produce carbon dioxide. So we will obviously see bubbling. So bubbling is seen. Okay. Describe a different test, the positive result that could be carried out to show that the acid was in excess. We can add blue litmus paper, and we know that blue litmus paper will turn red. It will turn red. Since it turns red, that shows that the acid is present, right? Next, another student used the apparatus shown to collect the volume of gas produced that the reaction between group 2 metal carbonate and excess hydrochloric acid. So this time is hydrochloric acid. Give two reasons why the second set of apparatus gives a more accurate measurement of the volume of gas given off. So first of all, you see over here, there is no bung replacement. So we can say that CO2 will not escape as the bung is being replaced. So there is no procedure like this, right? Instead, it will directly produce and it will be collected in the gas syringe, right? We don't have to like, press the bung again and then allow the carbon dioxide to be collected. Uh, Also, you can clearly see that the carbon dioxide is directly added up into the gas syringe, but over here, there was water. And carbon dioxide is slightly soluble in water, right? So the second thing is going to be CO2 get soluble in water because we don't have water to begin with over here, right? We don't have any water. Any carbon dioxide produced is going to be straight up absorbed in the gas syringe. All right. Next, the reaction of 0.320 gram of the group 2 metal carbonate is resulted in 89 cm cube of carbon dioxide gas being collected in the gas syringe. Okay, the equation is given. Determine by calculation the identity of the carbon group 2 metal carbonate using this data. Always remember the information that has been given, we will be using that to find the moles. Now, we cannot use this information to find the moles of this because this M is unknown. So we will be using this information to calculate the moles. Once we get the moles, we can find other things as well. So let's find out the mole of CO2 is going to be volume, which is 89.0 divided by molar volume, which is 24,000. We can see the value over here. Let's say 89 over 24,000, we get a value of 0.037, right? So we will be placing it as 0.037. 0.0037 mole. Now you see the mole ratio of carbon dioxide to the metal carbonate is 1:1. That means the metal carbonate will have a moles of 0.037, right? So mole of MCO3 0.0037. We already know that mole is equals to mass over molar mass. And our main target is to find the molar mass so that we can subtract the carbonate from the molar mass. We will be left behind with the mass of M and then compare which one of the group 2 metal has a molar mass of the calculated one and then write down the answer, right? So moles, if I want to subject molar mass over here, molar mass, mass is 0.320 over moles is 0.0037. We get a value of 0.320 over, what was the value? 0.0037. We get 86 point, let's say 5, 86.5, right? This is 86.5 gram per mole. Now, if I subtract mass of M will be 86.5 minus the mass of the carbonate. So 12 plus 16 times 3, we get a value of 26. 26. Now, the mass of 26 approximately is of magnesium. Therefore, we will say metal M is magnesium, as 26 is closest to 24, right? So magnesium is the answer. Next, bromoethane was prepared from the reaction of ethanol with sulfuric acid and potassium bromide. The equation is given over here. There are some procedures you need to get through. Step one, we add 10 cm cube of ethanol was placed in the round bottom flask. 10 cm cube of concentrated sulfuric acid was added to carefully and gradually to the ethanol in the flask. 12.0 gram of potassium bromide was added to the reaction mixture in the flask. The flask was set up for distillation and heated gently. Water and ethanol and bromoethane were collected in a small beaker. The bromoethane was purified. The bromoethane was dried. So when you are going to solve this paper, I would recommend you guys to skim through the steps, and as you solve the paper, you come back and read it again, right? And then write down the answers, right? For example, for the first one, suggest why the flask in step two was frequently placed in a stream of cold running water as sulfuric acid was gradually added. So in step two, as we were adding sulfuric acid, we were also placing it in the stream of cold running water, right? Why is that? It is because as you add your sulfuric acid, you don't want your ethanol to be evaporated quickly, right? So we write down the answer like this. Ethanol would evaporate, right? So to prevent that ethanol does not evaporate, we can't frequently place this in stream of cold running water. Why is that? Because the reaction might produce enough heat energy that will, like, evaporate the ethanol. The potassium bromide used in step three was initially lumpy and not a fine powder. Okay, state the apparatus that it would be suitable for breaking up the lumps of potassium bromide into powder. We make powder by using mortar and pestle. So we need something to grind them, and we use mortar and pestle to grind them. Explain why an orange color was seen in the round bottom flask when it was first gently heated. Now, orange color at the round bottom flask is due to any bromine that is being produced, right? Sometimes we might have some bromine producing over here because sulfuric acid is a good oxidizing agent, right? So some bromine was produced. Okay. All right. Next, complete the leveled diagram of the distillation apparatus used in step four, round bottom flask, and given over here, right? So for the distillation process, what we need to do is, okay, a different container to collect. And then we will have this as a condenser. Mind my drawing. I'm not Picasso over here, so sorry for the wobbly drawing, but this is how it is. And then we need to level this. This is water in, and this is water out, right? And this is the condenser that we're talking about. And this is where we collect, right? This is it. Identify the solid particles labeled A in the flask that have been added to promote smooth boiling. To promote smooth boiling, we add anti-bumping granules. So we write it down like this, anti-bumping granules. We use this anti-bumping granules for smooth boiling. We can also use glass beads as you wish, right? Bromoethane is a very volatile. So basically, the bromoethane is going to be collected over here in the container, right? And it is very volatile, such as what could be done with the small beaker used in step 5 to collect the bromoethane in order. We can have a ice bath, right? Or we can write down that put the beaker on ice water. So if we put the beaker on ice water, then ice water will actually allow the bromoethane to be as liquid because the temperature is going to be pretty much low and it will not be like, evaporated into a gas. Describe how to use a separating funnel to remove the aqueous layer from the bromoethane collected in step 5. So we see that bromoethane is a much more denser liquid, right? So if it is much more denser liquid, then we can add both of them in separating funnel, add both liquid in separating funnel, and there is going to be two layers, right? Two separate layers will form. And since we want to collect the bromoethane, oh, my bad. Uh, Separate. Since two layers are going to be formed and we want the bromoethane blend, we will actually open the tap and collect the bromoethane, right? So we'll write down, open the tap and collect bromoethane, which is the lower layer. Okay. State why bromoethane would not be dried in step 7 by placing in a warm oven. We don't want it to be a warm oven because bromoethane is volatile, right? So it would evaporate. It would evaporate. So we don't want it to be in a warm oven, right? A small quantity of water is removed by drying agent anhydrous calcium chloride. Complete the equation by writing down. Okay, so when this water is being added to this one, it gets hydrated. And this is how we write down hydrated salts. Cl2 dot 2H2O. So we show this water of crystallization as dots, right? State a chemical test for the OH group in the ethanol and a chemical test for the Br group in bromoethane. Include the expected positive observation. So for the test of OH group, we add PCl5, phosphorus pentachloride. Misty fume is seen. Misty fume is seen. We will see a misty fume of HCl, right? For bromide, we will add nitric acid followed by AgNO3. That AgNO3 is going to react with the Br aqueous and then produce a cream precipitate. It will produce a cream PPT. A cream precipitate, right? And that cream precipitate gives us the, it confirms the presence of a Br minus, right? A Br, okay. Third question, the equilibrium between iodine 1 chloride, chlorine, and iodine 3 chloride can be used to demonstrate the effect of changing condition on a system at equilibrium. Iodine 1 chloride is formed by passing chlorine over iodine in a U tube. The equation for this is shown. Okay. A further reaction then occurs between iodine 1 chloride and chlorine, which results in the equilibrium shown. This is the equilibrium. So we separate this and then further chlorine reacts to produce this ICl3, right? The apparatus shown can be used to set up and then demonstrate how the system and the equilibrium responds to changing condition. This is the apparatus where we can change the multiple things, and then after that we will see the observations, right? The addition of more liquid P to the flask on the left produces more chlorine gas. It will produce more chlorine gas. Explain the observation you would make as the amount of chlorine gas in U-tube increases. So you see, if I increase the chlorine, it will produce more brown, right? So basically, first of all, you see the chlorine is being added, so it will produce this. So if this one is increased, that means brown color is also observed. And you see this brown color will then react more with chlorine, and then it will produce a yellow solid, right? So first of all, we will see there are two things that is going to actually happen. First of all, brown liquid of ICl produced, and then yellow solid of ICl3 produced. And why does this happen? Because equilibrium moves forward side. The equilibrium, since equilibrium shifts to the forward side, we see that there is a yellow color solid, right? Because equilibrium shifts forward. Okay. All right. The three-way tap can be used to prevent more chlorine gas from entering the equilibrium system. Identify Q and state why it is necessary. So where is Q? So Q is over here, right? So why is it necessary? Because Q is going to a fume cupboard, right? Because we are adding chlorine gas more and more, and chlorine is toxic, right? So we will say that Q is fume cupboard. Why is it required? Because chlorine is toxic. You can say toxic, poisonous, whatever you feel like. Explain what you could do to YouTube to result in more brown liquid being absorbed. So basically, I want it to be more brown liquid, right? So if I want it to be more brown, I need to shift the equilibrium towards the backward side, right? So you see, the forward reaction is exothermic. If your forward reaction is exothermic, we can increase the temperature and the equilibrium will favor the side which is endothermic. In this case, it is backward, right? So we will simply increase the temperature, increase the temperature, equilibrium shifts to backward side. And we also need to reason. Equilibrium shifts to backward side because forward reaction is exothermic. Forward reaction is exothermic, right? Since the forward reaction is exothermic, increasing the temperature will favor the endothermic side, which is the backward. And since the backward side has ICl, which is the brown, which is the brown, and then after that, it will change the color to brown. More brown color would be observed. Sodium hydroxide solution absorbs excess chlorine. Write a equation for the reaction between cold dilute sodium hydroxide and chlorine. This is a very important equation which is given in the book Unit 2, and I would recommend you guys to memorize that equation. So sodium hydroxide NaOH, cold sodium hydroxide NaOH reacts with chlorine to give you two salts. Two salts are being produced, right? One is your chlorate one salt, which is NaClO, and the other one is sodium chloride, which is normal salt, along with water. This question frequently comes in questions, so I would recommend you guys to go through that. This happens for cold, right? And for hot, there is a different reaction that happens. It's nothing, it's just the oxidation of chlorine changes. We see chlorate 5 salt being produced along with sodium chloride and water. And due to that, we need to balance the equations further, right? This equation is not balanced yet. So to balance this equation, I need to put a 2 in front, right? Okay, moving on. An experiment was carried out to determine the enthalpy change of neutralization of the reaction between sulfuric acid and sodium hydroxide. So we are reacting this, and the procedure is given over here. So let's go through and then come back to the procedures. Give the reason why polystyrene cup in step one was placed in a beaker. So why do we need to place that in a beaker? Because we don't want the polystyrene cup to fall over, right? So we will write down so that polystyrene cup does not fall over. So we place it inside a beaker. State the purpose of measuring the temperature every 30 seconds for 2.5 minutes in step two. We want to do that so that we can make sure that the initial temperature is actually constant, right? So we will say to make sure initial temperature is constant. You can write down constant, you can write down consistent, or even to determine the initial temperature, right? Explain why the temperature was not measured at 3 minutes. So basically, we did not measure the temperature when it was like, third minute. In the third minute, we did not measure any temperature. Why is that? Because we want to have some sort of change in temperature, right? So during that 3 minute, the temperature was actually changing, and it takes some time for the temperature. Sorry, it takes some time for the alkali to be added, right? We are adding 50 cm cube, right? So let's write down the answer. Some time to add 50 cm cube of NaOH. Okay, the data from the experiment was shown on the graph. For the simplicity, I have already drawn this straight line. You would require to draw the straight line in your main exam as well. Determine the maximum temperature change and del T for this reaction using the graph. You must show the working in your graph, right? So this is the diagram, and we can see the maximum temperature over here. The maximum temperature is, it reads 35 degrees Celsius. So we will write down 35 degrees Celsius. Explain why the temperature decreases over time after 5 minutes. So basically, after adding up and during after 5 minutes, why does it decrease, right? It decreases because no more reaction is actually happening. All the reaction is done. The further that we are adding, it is just not increasing the reaction. As I mean, like the reaction is not happening, right? So we will write down no reaction occurs. And since no reaction is occurring, the heat energy, this is actually gradually being lost to the surrounding. And heat is lost to the surrounding. Heat energy is actually lost to the surrounding. Give a possible reason why the temperature does not appear to change at various times, such as 5.5 minutes and 6.5 minutes. So basically, you see there are some straight lines like this, right? See? In 5.5 minutes and 6.5 minutes, it does not actually change. We will write it down like this because the thermometer that we used might not be precise enough to record this small change in the temperature, right? So we will say the sorry, the thermometer is not precise enough. If the thermometer was precise enough, we would actually record very small change in temperature, right? State why the data will not result in the standard molar enthalpy of neutralization being calculated. Okay, so for standard enthalpy change, the temperature has to be 298 Kelvin or 25 degrees Celsius, and the pressure has to be 100 Kelvin, right? I mean, like kilopascal, my bad, 100 kilopascal. But if we look at the diagram, where is it? If we look at the graph, we see that the starting temperature is actually about 23, right? So since it is starting is 23, that means that this is not standard. So we will say starting temperature is not 25 degrees Celsius. Okay. Next, when calculating the enthalpy change of neutralization, the two expressions used are this. Explain why it may or may not be valid to assume that the specific capacity of water is suitable to be used. So they are asking why it may be valid, or they are also asking that why it might not be valid, right? So it's kind of like you can write both. Okay. So first of all, we can say that the the substances that are being produced are what is it? It's a salt, right? It's sodium sulfate salt along with water. And also the reaction that is actually happening is between sulfuric acid and sodium hydroxide, which are not water, right? So we will say that the specific heat capacity of salt is not the same as water, so it is not valid. So if you want to write down that whether it is not valid, you write down that the assumption is not valid. And if you want that this is going to be valid, so you will say that most of the acid and alkali are usually water. I mean, like it is not that highly concentrated, so it contains most of it is water, so it might be valid, right? So we can write down that as well. State why the number of moles of sodium hydroxide and not the number of moles of sulfuric acid is used in the calculation of this experiment. Because you see, the number of moles of sodium hydroxide is the same that of water. For neutralization to take place, we say that it is the enthalpy change when 1 mole of water being produced, right? So water has to be consistent. So the 1 moles that is consistent with water is that of the moles of sodium hydroxide. So we can say that the number of moles of NaOH is same as that of water. Okay, so that concludes our this paper. So I will be posting some more of the papers as well as for Unit 4, 5, and 6. So I would encourage you guys to watch those ones as well. And once again, uh, thanks for watching.